In this video, we're going to talk about AC circuits and impedance. So the first thing you need to know is that the RMS voltage is equal to the peak voltage divided by the square root of 2. And RMS current is equal to the peak current divided by root 2. Now let's say if we have an AC source connected to a resistor. In this circuit, energy is transformed into heat. The current and the voltage are in phase. So voltage is equal to current multiplied by resistance, and the average power consumed in this circuit is simply voltage times current. So let's work on the problem. Let's say if we have a 120 volt AC source. And let's say that the resistance is 100 ohms. What is the current that flows in this circuit? So using the equation V is equal to IR. The voltage is 120. The resistance is 100. So 120 divided by 100, the current in the circuit is 1.2 amps. Now how much power is dissipated by the resistor? So power is equal to voltage times current. The voltage across the resistor is 120 volts, and the current that it uses up is 1.2 amps. So 120 times 1.2 is 144 watts. Now, let's say if we have an AC signal that is an alternating current attached to an inductor, which has this symbol. The inductor has the inductance, let's say, 50 millihenries. What equations apply in this circuit? Inductors present inductive reactance to an AC circuit, which acts like resistance. The inductive reactance, represented by XL, is equal to 2 pi FL. XL is measured in ohms like resistance. So just as V equals IR, V is equal to I times XL. If you were to plot a graph between the frequency and the inductive reactance, these two are directly related. As the frequency increases, the inductive reactance increases as well. So when F goes up, XL goes up. And as the inductive reactance goes up, the current in the circuit decreases. Current and inductive reactance are inversely related. So high frequency AC signals will yield less current in the circuit, and low frequency signals could pass more current in the circuit. Now going back to this equation, where inductive reactance is equal to 2 pi FL, you need to know that omega, the angular frequency, is equal to 2 pi F. So XL can be represented as omega times L. So just keep that in mind. Also, for an inductor, the current lags the voltage by 90. You need to know that as well. So whenever you have an AC signal passing through an inductor, the AC signal, the current in it is changing. It's increasing and decreasing. It's not constant. And because the current changes, you're going to have a change in magnetic flux inside the inductor. As the current increases, the energy stored in the inductor increases as well. And as the current decreases, the energy stored in the inductor decreases. So energy is stored in the inductor temporarily. The inductor stores energy in this magnetic field, and then it releases it back as the current in the circuit increase and decrease. So in the case of a resistor, energy in a resistor is dissipated as heat, so that energy is gone. But in the case of an inductor, the energy is not gone. It is stored temporarily in the magnetic field of the inductor, and then it is released back to the source. Therefore, For all practical purposes, the inductor doesn't consume energy. It simply stores it and gives it back. So there's no loss in energy. Now granted, no inductor is perfect. There's going to be some resistance in the coils of the inductor. And that resistance will dissipate energy as heat. But assuming if the inductor has no resistance, then it dissipates no energy. It simply stores it temporarily. Now let's talk about frequency. Let's say if the frequency of the AC signal is 60 Hz. What does that mean? This means that the alternating current changes direction 60 times in 1 second. Frequency is the number of cycles per second. So the current changes direction 60 times per second. Let's say if the frequency was 5 kilohertz. This is equal to 5,000 hertz. That means that the AC signal changes direction 5,000 times in a single second. So whenever you see the word frequency in terms of an AC signal, that's what it means. Now let's move on to a capacitive circuit. Capacitive reactance is 1 over 2 pi Fc. And we know that omega is 2 pi F. So capacitive reactance is 1 over omega times C. So as the frequency increases, the capacitive reactance decreases. Notice that F is on the bottom of the fraction. So F and XC, they're inversely related. If we were to plot a graph between the capacitive reactance and the frequency, here's how it will look like. As the frequency goes up, the capacitive reactance goes down. So it's an inverse relationship. And the voltage in the circuit is equal to the current multiplied by the capacitive reactance. The capacitive reactance, like the inductive reactance and resistance, they all have the same unit, and that is ohms. So just keep that in mind. By the way, for a capacitive circuit, the current leads the voltage by 90. For an inductive circuit, the current lags the voltage by 90. Now, just as an inductor can store energy temporarily in its magnetic field, the capacitor can store energy temporarily in its electric field. In an AC circuit, the voltage is constantly increasing and decreasing. It's basically a sine wave. The voltage goes up, then it goes down, and so forth. Whenever the voltage is increasing, the capacitor is storing energy. It's being charged. It's storing energy in its electric field. And when the voltage decreases, the capacitor releases that stored energy. Because it absorbs and releases energy just like an inductor, the capacitor doesn't consume energy. So only the resistor consumes energy. It loses energy as heat. It doesn't give it back. But capacitors and inductors, they store energy temporarily. So they dissipate no energy. Now let's work on some problems. Number 1, the peak voltage of an AC signal is 170 volts. And the RMS current is 5.4 amps. What is the RMS voltage? What is the peak current? To calculate the RMS voltage, it's simply equal to the peak voltage divided by the square root of 2. The peak voltage is greater than the RMS voltage, and that's always going to be the case. So it's 170 volts divided by root 2. So this is equal to 120.2 volts. Now part B, what is the peak current? The RMS current is equal to the peak current divided by the square root of 2. So if we rearrange the equation by multiplying both sides by root 2, the peak current is equal to the RMS current times root 2. So it's going to be the square root of 2 times 5.4 amps. So this is going to be about 7.64 amps. So the peak current is always greater than the RMS current. And the RMS voltage, or the RMS current, is always less than the peak value. Number 2, at what frequency will a 250 millihenry inductor have an inductive reactance of 700 ohms? So feel free to try this problem. The inductive reactance is equal to 2 pi times the frequency times the inductance. The inductive reactance has unit ohms, so it's 700 ohms. We're looking for F, the frequency. And L is the inductance of the inductor, which is measured in henries, or in this case millihenries. So 250 millihenries is basically 0.25 henries. You got to divide it by 1,000 to convert millihenries to henries. So the frequency is going to be 700 divided by 2 pi times 0.25. So it's going to be about 445.6 hertz. This frequency will produce an inductive reactance of 700 ohms. Number 3, a 60 hertz AC signal at 120 volts is connected across a 500 millihenry inductor. Calculate the inductive reactance. So let's begin by drawing a picture. So here's the AC signal, and here is the inductor. So the voltage is 120, and the frequency is 60 hertz. And the inductance is 500 millihenries. So to find the inductive reactance, let's use this equation. It's 2 pi times F times L. So the frequency is 60, and L, 500 millihenries, that's the same as 0.5 henries if you divide it by 1,000. So 60 times 0.5 is 30, times 2 pi, that's 60 pi, which is 188.5 ohms. So that's the inductive reactance. Once we have that, we can find the current in the circuit. So V is equal to I times XL, which means that the current is equal to the voltage divided by the inductive reactance. The voltage is 120, and the inductive reactance is 188.5. So the current in the circuit is 0.6366 amps. Now what about part C? How much power is dissipated in the inductor? The inductor doesn't dissipate anything, so it's 0 watts. It simply stores energy temporarily in its magnetic field, and then it releases it back. And it's constantly doing it. It's constantly absorbing energy and releasing energy. So it doesn't consume energy. Number 4, a 1.5 kilohertz AC signal at 30 volts is connected across a 100 microfarad capacitor. Calculate the capacitive reactance. So here is the AC signal, and it's directly across a capacitor. So the signal is at 30 volts and 1.5 kilohertz. And the capacitance is 100 microfarads. So let's begin by calculating the capacitive reactance, which is Xc, and is equal to 1 divided by 2 pi Fc. So it's 1 over 2 pi times the frequency. 1.5 kilohertz is 1500 hertz. You got to multiply it by 1,000 to convert it to hertz. And 100 microfarads is basically 100 times 10 to the minus 6 farads. So anytime you hear the word kilo, it's 10 to the 3. Mega, 10 to the 6. Milli, 10 to the minus 3. Micro, add 10 to the negative 6. So if we multiply 2 pi times 1500 times 100 times 10 to the minus 6, you should get 0.9425. And 1 divided by that number is 1.061. So this is the capacitive reactance of the circuit. Now what is the current in the circuit? So V is equal to I times XC, which means I is V over XC. So it's 30 volts divided by 1.061 ohms. So this yields a current of 28.3 amps. So that's the answer to part B. Now part C, how much power is dissipated by the capacitor? Like the inductor, the capacitor doesn't dissipate anything, so it's 0 watts. It stores energy in its electric field and then temporarily releases it back. So this is the answer to part C. Number 5. A 500 Hz AC signal at 60 volts draws a current of 2.5 amps when connected across an inductor. What is the inductive reactance? So let's make a list of what we have. We know the frequency is 500 Hz. And we have the voltage. The voltage is 60 volts. And we also know the current, which is 2.5 amps. So what we're looking for is the inductive reactance and also the inductance. Well, we know that V is equal to I times XL. So XL is the voltage divided by the current. 60 volts divided by 2.5 amps. So 60 divided by 2.5, that gives us an inductance, or an inductive reactance rather, of 24 ohms. So that's the answer to part A. Part B, what is the inductance? So once we have XL, we can use this equation to find L. So 24 is equal to 2 pi times the frequency of 500 times L. 2 pi times 500 is 1000 pi. So L is going to be 24 divided by 1000 pi. And so L is 0.00764 henries. To convert that to millihenries, multiply by 1000. So it's about 7.64 millihenries. So that's the inductance. Now, there are some other circuits that you need to be familiar with. Let's talk about 3 different types. One circuit contains a resistor, an inductor, and also a capacitor. So this circuit is known as an RLC circuit because it has all 3 elements. The other 2 looks like this. So on the left, we have a resistor and a capacitor. So that's known as an RC circuit. On the right, we have a resistor and an inductor. So it's known as an RL circuit. For each of these circuits, Z, which is the impedance, is equal to the square root of R squared plus XL minus XC squared. So for an RLC circuit, that's the equation that you're going to have. For an RL circuit, there is no XC. XC is 0, so it's just going to be R squared plus XL squared. And for an RC circuit, there is no XL. Z is going to be R squared plus XC squared. Now let's go back to the RLC circuit. The voltage across the resistor is known as VR, and this is equal to the current multiplied by the resistance. The voltage across the inductor, this is known as VL, and it's equal to the current times the inductive reactance. And the voltage across the capacitor, VC, that's going to be equal to the current in the circuit times the capacitive reactance. Now, if you want to find the current that flows in the circuit, the current is going to be the voltage divided by the impedance, Z. R is the resistance in ohms. XL is the inductive reactance, which is also in ohms. XC, the capacitive reactance, is in ohms. Z connects R, XL, and XC together, as we've seen in this equation. So Z is a type of, it has the same unit of resistance. So just as V equals IR, V is equal to IZ. So that's how you can find the total current in the circuit. Just take the voltage divided by the impedance. Now there are some other equations that you need to know. So if you want to find the phase angle, it's XL minus XC over R, well, tangent of the phase angle. And the phase angle is going to be the arctan of the inductive reactance minus the capacitive reactance over the resistance. You can also use this equation. Cosine of the phase angle is equal to the resistance divided by the impedance. Cosine of the phase angle is also known as the power factor. Now, to calculate the power dissipated by the circuit, it's equal to I squared times R. Keep in mind, only the resistor dissipates energy. The inductor and capacitor, they both temporarily store it and then release it. So the power that is absorbed by the circuit is I squared R. You can also use this equation. It's equal to the average power is the RMS current, and the voltage RMS value times the power factor. So you can also calculate the average power using that formula. And that's basically it. These are the main formulas that you need to know for the RL circuit, the RC circuit, and the RLC circuit. Now, whenever you have a circuit with a capacitor and an inductor, be it an LC circuit or an RLC circuit, you can calculate the resonant frequency, which is 1 over 2 pi square root LC. At the resonant frequency, the capacitive reactance and the inductive reactance are equal to each other. So in that case, the impedance, which is the square root of R squared plus XL minus XC squared, since XL minus XC are the same, these two will cancel. XL minus XC is 0. So Z is equal to R. So at the resonant frequency, make sure you know that capacitive reactance equal inductive reactance, XC equals XL, and Z, the impedance, is just the resistor, the resistance of the resistor. Number 6. A 800 Hz AC signal at 100 volts is connected across an RL circuit consisting of a 300 ohm resistor and an 80 millihenry inductor. Calculate the inductive reactance. So let's draw the circuit first. So we have a resistor and an inductor. So the frequency of the signal is 800 Hz, and the voltage is 100 volts. Now we have a 300 ohm resistor and an 80 millihenry inductor. So to find the inductive reactance, we can use this equation. XL is equal to 2 pi FL. So that's 2 pi times the frequency of 800 times L, 80 millihenries, or 80 times 10 to the minus 3. If you see milli, you could just add 10 to the negative 3 to it. That's a quick way to convert it. So XL is equal to 402 ohms, or 402.1 ohms. Now let's calculate the impedance. The impedance is going to be the square root of R squared plus XL minus XC squared. Since there's no capacitor in the circuit, XC is 0. So R, the resistor, has a value of 300 ohms, and XL is 402.1. So the impedance of the circuit is 501.7 ohms. Now let's move on to part C. What is the current in the circuit? To find a current, it's simply equal to the voltage divided by the impedance. The voltage is 100 volts. The impedance is 501.7 ohms. So this is equal to 0.199 amps. So that's the current in the circuit. Now what about part D? What is the phase angle? To calculate the phase angle, we can use this equation. Arctan XL minus XC over R. So in this case, XL, we can see that it's 402.1. XC is 0. And R, that's 300 ohms. So arctan 402.1 divided by 300. Make sure your calculator is in degree mode, by the way. This will give you a phase angle of 53.3 degrees. Now there's another way in which we can calculate the phase angle. We can use this formula as well. It's equal to the arc cosine of R divided by Z. So the resistance is 300 and the impedance, that was 501.7. I believe that was the number that I used before. So if you type in arc cosine 300 divided by 501.7, this will give you the same answer of 53.3 degrees. So that's the phase angle. Now what about part E? Calculate the power dissipated by the circuit. A simple way to do that is to use this equation. It's I squared times R. So we know that the current is 0.199 amps and the resistance is 300 ohms. So 0.199 squared times 300, that's about 11.9 watts. So that's the power dissipated by the circuit. Now, in addition to using this equation, you can use this equation. It's equal to the RMS voltage times the RMS current multiplied by the power factor, cosine of the phase angle. So the voltage is 100. The current in this circuit is 0.199 times cosine of 53.3. And this will give you the same answer of 11.9 watts. And so that's it for part E. Number 7. A 2.5 kilohertz AC signal at 60 volts is connected across a RC circuit consisting of a 50 ohm resistor and a 1.5 microfarad capacitor. Calculate the capacitive reactance. So we have a resistor and a capacitor. And we have a 2.5 kilohertz signal, that's the frequency. And the voltage is 60 volts. Now we also have a 50 ohm resistor and a 1.5 microfarad capacitor. So let's start with part A. The capacitive reactance, we know it's 1 divided by 2 pi Fc. So that's 1 divided by 2 pi times the frequency, 2.5 kilohertz, that's basically 2.5 times 10 to the 3. And then the capacitance C, that's 1.5 microfarads, or 1.5 times 10 to the negative 6 farads. So type it in your calculator exactly the way you see it, and you should get 42.4 ohms. So that's the capacitive reactance. Now let's calculate the impedance. So the equation is R squared plus XL minus XC squared. In this problem, XL is 0, there's no inductor. So it's just going to be the square root of 50 squared plus 0 minus 42.4 squared. But once you square it, the negative sign will disappear. So the impedance is about 65.6 ohms. Now once we have the impedance, we can calculate the current. The current is simply going to be the voltage divided by the impedance. So it's 60 volts divided by 65.6 ohms. Which is about 0.915 amps. So that's the current in the circuit. Now to calculate the phase angle, it's going to be arctan XL minus XC. XL 0, XC is 42.4 divided by R, which is 50. So it's arctan negative 42.4 divided by 50. So that gives us an angle of negative 40.2 degrees. Now let's also calculate it the other way. Let's use this equation, arc cosine R over Z. R is 50 ohms, Z is 65.6. And this will give you a positive angle, which is about 40.3. So which one is correct? Is the answer negative 40 or positive 40? It turns out that the phase angle is negative for any RC circuit. For a circuit that's more capacitive than inductive, the phase angle will be negative. For an RL circuit, the phase angle should be positive. Now, let's focus on part E. Let's determine the power dissipated by the circuit. And let's use two equations to get the answer. So first, the power is going to be I squared times R. We have the current, it's 0.915, and we know the resistance is 50. So 0.915 squared times 50 is about 41.9 watts. Now let's use the other equation to get the same answer. So let's multiply by the RMS voltage times the RMS current times the power factor. The voltage is 60, the current is 0.915, and cosine of negative 40.2. Cosine negative 40.2 and cosine 40.2 did the same. This will give you the same answer of 41.9 watts. So you can use both equations to calculate the power dissipated by this circuit. Number 8. A 1200 Hz AC signal at 50 volts is connected across a RLC circuit consisting of a 100 ohm resistor, a 0.5 microfarad capacitor, and a 12 millihenry inductor. Calculate the inductive reactance. So if you wish to draw a circuit, we have a resistor, we have an inductor, and a capacitor. So that's the circuit that we have in this problem. So the inductive reactance, XL, that's going to be 2 pi FL. So that's 2 pi times the frequency, which is 1200, times the inductance, 12 millihenry, so that's 12 times 10 to the minus 3. So that's going to be about 90.5 ohms. So I'm going to put the inductive reactance right next to the inductor. Now let's calculate the capacitive reactance, XC. This is equal to 1 divided by 2 pi FC. So it's 1 divided by 2 pi times the frequency of 1200 times the capacitance, which is 0.5 times 10 to the minus 6. And so that's going to be about 265.3 ohms. So now we can find the impedance. Z is going to be the square root of R squared plus XL minus XC squared. So let's plug it in. R is 100. XL is 90.5. XC is 265.3. So first, let's subtract 90.5 minus 265.3. That's negative 174.8. Once you square it, you're going to get a positive number, and then add 100 squared to it. So you should have 40,555, and then take the square root of that result. So the impedance of the circuit, which I'm going to write it here, it's 201.4 ohms. So now let's just make some space. Let's get rid of this stuff. We don't need it anymore. Part D. What is the current? The current is the voltage divided by the impedance. The voltage of the circuit is 50 volts. So it's going to be 50 volts divided by 201.4 ohms. So that's 0.248 amps. Now that we have the current, let's calculate the phase angle. So the phase angle is arctan XL, which we know it to be 90.5, minus XC, which is 265.3, divided by R. And R is 100 ohms, which is given to us in the problem. So notice that XC is larger than XL. So the circuit is capacitive, which means that the phase angle is going to be negative. So arctan 90.5 minus 265.3, That's negative 174.8. So it's arctan negative 174.8 divided by 100. And you should get an angle of negative 60.2 degrees. So that's the answer to part E. Now the last part, the power dissipated by the circuit, is simply equal to I squared times R. We know the current is 0.248 amps, since we have it here. And the resistance is 100 ohms. So 0.248 squared times 100. That's going to be about 6.15 watts. Now, just to confirm our answer, just to make sure that it's correct, let's calculate the power using the other equation. If the two answers match, that means that we've done everything correctly. If they don't match, we messed up somewhere. So the RMS voltage is 50 volts. The RMS current, 0.248 amps. And then it's going to be cosine of the phase angle, which is negative 60.2. So 50 times 0.248 times cosine negative 60.2. That's equal to the same thing, 6.16. Now, the slight difference is due to rounding intermediate answers. So if you plug in the exact answers, these two should be exactly the same. But they're very close enough, so that's it for this problem. Now, let's go ahead and calculate the voltages across every element. That's one more thing I almost forgot to do in this problem. Now, 50 divided by 201.4, we round it to 0.248, but let's use 0.2483 to get a more accurate answer. So first, let's find the voltage across the resistor. Then we'll find the voltage across the inductor, VL, and also the voltage across the capacitor. The voltage across the resistor is simply I times R. The current is 0.2483, and the resistance is 100 ohms. So that's going to be 24.83 volts. So that's the voltage across the resistor. Next, let's find the voltage across the inductor. It's going to be I times XL. So the same current of 0.2483 times the inductive reactance of 90.5. So this will give us a voltage of 22.471 volts. So that's the voltage across the inductor. Now the voltage across the capacitor, the magnitude is going to be the current times XC. So the current is 0.2483 and the capacitive reactance is 265.3. Here it is. So that's going to be 65.87 volts. In a DC circuit with resistors, the voltage drop across each resistor typically would add up to the voltage of the source. But in an RLC circuit, it's different. If we add up these three voltages, they do not add up to 50. Notice that the voltage across the capacitor is greater than the source voltage of 50. So these voltages are related by a different equation. Vs, the voltage source of 50, does not equal VR plus VL plus VC. That doesn't happen in this circuit. But rather, they are related to each other by this equation. Vs squared is equal to VR squared plus VL minus VC squared. The same way as Z squared is equal to R squared plus XL minus XC squared. And let's go ahead and check to make sure that all of our answers are correct. So Vs is 50 squared, VR is 24.83 squared, VL, that's 22.471, minus VC, which is 65.87, and then squared. So first, let's get rid of some stuff. $50 squared is 2,500. 24.83 squared, that's about 616. 22.471 minus 65.87, that's negative 43.399. Now let's go ahead and square that number. So this is going to be 1883.5. And if we add it to 616.5, we can see that 2500 equals 2500. So the voltages across the resistor, the inductor, and the capacitor is related to each other by this equation. Number 9. A LC circuit consists of a 50 millihenry inductor and a 100 microfarad capacitor. What is the resonant frequency? So let's draw a circuit. So here's our AC source, and there is an inductor L and a capacitor C. So that's a typical inductor capacitor LC circuit. Now the equation to calculate the resonant frequency is 1 over 2 pi square root LC. So all we need to do to find it, to answer part A, is just plug in the data that we have. So we know the inductance, 50 millihenries is 50 times 10 to the minus 3 henries. And then the capacitance is 100 times 10 to the negative 6 farads. So all you got to do is type this in. But let's take it one step at a time. Let's multiply 50 times 10 to the minus 3 by 100 times 10 to the minus 6. That's 5 times 10 to the negative 6. If you take the square root of that and then multiply it by 2 pi, you should get 0.01405. And if you raise it to the negative 1 power, this will give you the resonant frequency, which is about 71.2 hertz. Now keep in mind, at the resonant frequency, XL is equal to XC. The inductive reactance is equal to the capacitive reactance. And in fact, using this expression, you can derive this equation. Let's go ahead and do that. So XL is equal to XC. XL is 2 pi FL. XC is 1 over 2 pi FC. Now what we're going to do is, let's multiply both sides by F. So on the right side, these two will cancel. On the left side, F times F is F squared. So we're going to have 2 pi L times F squared, and that's equal to 1 over 2 pi C. Now let's multiply both sides by 1 over 2 pi L. On the left side, 2 pi L will cancel. So we're going to have F squared is equal to 1 over 2 pi times 2 pi is 4 pi squared, and then times LC. So now let's take the square root of both sides. The square root of F squared is F. The square root of 4 is 2. The square root of pi squared is pi. And the square root of LC is just square root LC. And so that's how you can derive this equation. Now let's work on part B. What capacitance is required to produce a LC circuit with a resonant frequency of 1500 Hz if L, the inductor, is 15 millihenries? So let's start with this equation. And our goal is to solve for C. So let's begin by squaring both sides. If we take the square of both sides, we can see that the resonant frequency, the square of the resonant frequency, is equal to 1 over 4 pi squared times LC, which we had this equation not too long ago. So now what we're going to do is multiply both sides by C. And so on the right side, these will cancel. And so we have C times F squared is 1 over 4 pi squared times L. Now let's multiply both sides of the equation by 1 over F squared. So these two will cancel. And on the right, we're just going to multiply this by F squared. So we're not going to have F squared on the left side anymore. So C is equal to 1 over 4 pi squared times F squared times L. So that equation will help us to calculate the capacitance in an LC circuit at resonance. So the frequency is 1500 Hertz, and L is 15 times 10 to the minus 3. So 15 times 10 to the minus 3 times 1500 times 4 pi squared. That's equal to 888.26. So 1 divided by that result will give us a capacitance of 1.126 times 10 to the minus 3 farads. 10 to the minus 3 is the same as milli, so this is about 1.13 millifarads. Or if you want it in microfarads, multiply by 1,000. That's 1130 microfarads. So that's the capacitance required to produce an LC circuit with this resonant frequency. Number 10. A 12-volt AC signal is connected across a RLC circuit consisting of a 50 ohm resistor, a 7.04 nanofarad capacitor, and a 900 millihenry inductor. Determine the resonant frequency of the circuit. So let's draw a picture. So we have a resistor, a capacitor, and an inductor. So the voltage is 12 volts. And the resistance is 50 ohms. Let's calculate the resonant frequency to begin. It's going to be 1 divided by 2 pi times the square root of LC. In this problem, L is 900 millihenries, or 900 times 10 to the minus 3. And the capacitance is 7.04 nanofarads, or 7.04 times 10 to the minus 9 farads. So you should get a resonant frequency of, if we round it, 2000 Hertz, or simply 2 kilohertz. So let's put that here. Now let's focus on part B. What is the inductive and capacitive reactance at this frequency? So let's start with the inductive reactance, which is 2 pi F times L. So that's 2 pi times a frequency of 2000 Hertz times the inductance, which is about 0.9 henries, or 900 times 10 to the minus 3. So XL is about, if we round it, 11,310 ohms. So let's put that here. We're going to say it's 11.3 kilo ohms. Now let's calculate XC. XC is 1 over 2 pi FC. So that's, in your calculator you can type like this: 1 divided by parentheses 2 pi times a frequency of 2000 hertz times a capacitance of 7.04 times 10 to the minus 9. So you're going to get also 11,304. I'm going to round that to 11.3 kilo ohms. So as you can see, these two are very close. If the circuit is perfect at the resonant frequency, the capacitive reactance should equal the inductive reactance. Now in this example, we have some rounding errors, but it's close enough. We can work with that. Now what about part C? What is the impedance and the current in the circuit? At the resonant frequency, the impedance is equal to R. So it's going to be 50 ohms. And here's how you know. We know that Z is equal to the square root of R squared plus XL minus XC squared. So this is going to be the square root of 50 squared. XL is 11,300 if we round it. XC is also 11,300. Because they're the same, XL minus XC is 0. So the square root of 50 squared plus 0, which is the square root of 50 squared, that's simply equal to 50. So, under perfect conditions, at the resonant frequency, the impedance is simply equal to R. So now that we have the impedance, we could find the current. The current's going to be the voltage divided by the impedance. So we have 12 volts, and the impedance is 50. 12 divided by 50 will give us a current of 0.24 amps. Now let's calculate the phase angle. So this is going to be arctan, or inverse tan, XL, which is 11,300, minus XC divided by R. So basically this is inverse tan of 0. Arctan of 0 is 0. So at the resonant frequency, the phase angle is 0. Now what is the voltage across each element? So we have a current of 0.24 amps. Let's use that information to find the voltage across the resistor, the capacitor, and the inductor. The voltage across the resistor is going to be I times R. So the current of 0.24 amps times a resistance of 50 ohms. And that's equal to 12 volts. So that's the voltage across the resistor. Notice that it's equal to the voltage of the source, because the other two voltages, they're the same and they're going to cancel out. Now to find the voltage across the capacitor, it's going to be I times XC. So that's the current of 0.24 amps times 11,300 ohms. And this will give you a voltage of 2712. Now, VL, which is I times XL, is going to give you the same answer. You have a current of 0.24 and an inductive reactance of 11,300. So you're going to get 2712 volts. Notice that the voltage across the capacitor and the inductor is very, very high. As you can see, it's significantly higher than the voltage of the source. The voltage of the source is only 12 volts. The voltage across the capacitor and the inductor is 2,700 volts. It's much, much higher. In fact, more than 100 times higher. So, very high voltages can be produced in an RLC circuit. So just keep that in mind.